everybody, welcome to the video for properties of tangents. Okay guys, in this video we're going to tackle tangent segments. This is the last video for properties of circles, so we're going to go ahead and tackle the properties of segments that are external to a circle called tangents. We're going to apply the properties of tangents to circles to find missing links and measurements. Tangents form structural supports for engineering projects and are important in design and construction. So this is why we're going to do this, so let's get to it. So, what is a tangent? A tangent to a circle is a line or line segment. It could also be a ray that touches the circle exactly once at the point of tangency. So you can see from the diagram, the tangent is the line itself. The point of tangency is the single point that the circle actually and the circle and the line actually touch. If you look at the circle and the line, it looks like the circle and the line overlap at some other points too, but they do not. It's just incredibly close so that our eyes really can't tell the difference. The exact point of tangency is the only specific location that those things actually intersect. So, we're going to talk about an additional segment type. The additional segment type is called a secant. A secant is a line that intersects a circle in exactly 2 points. That sounds just like a chord, right? A chord starts and ends on the circumference of a circle. But unlike a chord, it may not end on the circumference of the circle. So if you look at the two examples that I have of secants on the left, one of them is a ray starting on the circumference of the circle on the left, and then it crosses through the circle circumference on the right, and it continues. So that is an example of a secant. Another example of a secant, it looks like a chord, but instead of ending on the circle, it continues through the circle in both directions. So notice that even though they intersect the circle twice, they're not chords because they continue outside of the circle. And then I put a chord on the right for the just so you could differentiate between the two. A chord, remember, is a line segment, where secants are going to be rays or just full-on lines. So, let's go over some properties of tangents. This one is called the tangent radius property. A radius drawn to the tangent. So basically, if you have a tangent and you draw the radius from the center of the circle to the point of tangency, and it hits the tangent, that means that radius will always be perpendicular to the tangent. So it will always form a 90-degree angle with the tangent. So in summary, or in short, because AB is a radius and CD is a tangent, angle ABC and angle ABD are both 90-degree angles. And this applies to any tangent and any radius that you draw. So now we're going to talk about the two tangents property. The two different tangent line segments, or lines, that converge to a single point outside the circle are guaranteed to be congruent. So, because JH and FH converge, meaning they're going to the same single location, it is guaranteed that the segment FH and JH are congruent. If you look at the figure, if you look at like the diagram here, what kind of figure is partially inscribed in the circle? If you look at it, we have like 90-degree angle here, and we have a 90-degree angle here. Well, what kind of shape are we looking at? I have two congruent segments here, two congruent angles across from each other, and I know that these the radii are also congruent. So what kind of figure is this? We're thinking back to Unit 6 when we did the properties of quadrilaterals. That's a kite. We have a kite. So when we see this familiar figure, we can think about the properties of kites. We know that these angles are congruent and add up to 180. And then shortcut, A and H have to add up to 180 as well, since 180 out of 360 is taken. So in this situation, we know that angle A plus angle H out here add up to 180 degrees in this kite. So we have some additional information that might help us find angle measurements later. Okay, continuing. Tangent circles. So we're not going to spend too much time on this, but I just wanted to go over the concept. Tangent circles are two circles that are tangent to the same line at the same point. So take a look at this. If like the green circle and the orange circle are internally tangent, because the green circle is inside of the orange circle, but they still only touch at this point here. And then you have the red circle is externally tangent to the orange circle because, again, they only touch at that one unique point right there. And they share this black tangent line here. So we're just going to jump right into some different examples that we can have and do from the different types of tangents. So let's read this out loud. In the figure, ray AB, so we have ray AB on the top, is tangent to circle C at point B. Okay, so this is the point of tangency here. So this is my point of tangency. Point of tangency. The length of the segment AB is 15, so from A to B is 15, and the length of AC is 17, so the whole thing is 17. What is the measure of radius CB? Okay, so let's see. I do notice, okay, so I'm thinking through this, and I do notice that this shape here, so I do know that ABC is a triangle. That may help me, so that's something that I know. The next thing I know is that CB is a radius, so that's important to add in there. So I'm going to add that information here. CB is a radius. And so that means I'm going to use the tangent radius property. Tangent radius property. So the tangent radius property tells me that BC, segment BC and segment AB would intersect at a 90-degree angle. Well, if I have a 90-degree angle, then that tells me that after all of that, we have a right triangle, which means I'm going to use the Pythagorean theorem. So let's use the Pythagorean theorem, and we're going to label this as A, because it's one of the 90-degree angle legs, in order to find the measure of BC. So A squared plus 15 squared, because that's side B, the other leg, equals 17 squared. So I get A squared plus 225 equals 289. So when I subtract 225 from both sides, I get A squared equals 64. And then I'm going to take the square root of both sides, so that A equals 8. So I can say that BC, the measure of BC, is 8 through calculations with the Pythagorean theorem. Okay, so again, we have another Pythagorean theorem, and you might even recognize some of the Pythagorean theorem type problem, because you can already see that there's a right angle listed and it's a right triangle. But this one is a little bit different, okay? It says in circle C, AB is tangent to the circle at point B, so we have our point of tangency here. And I'm actually going to highlight it in red so that you guys can kind of see what I'm talking about. What is the measure of AD, the external segment of the circle? So they're looking for this measure right here. Okay, well, we kind of already just saw how this is going to turn out Pythagorean theorem-wise. We're going to go ahead and solve for AC. AC here is the hypotenuse. So we're going to solve for that. And then we will come back to finding segment AD in a bit. So 8 squared plus 15 squared equals C squared. So I get 64 plus 225 equals C squared. So I get 289 equals c squared. So 17 equals c. Okay, so I know that the entire length here, okay, is 17. But I don't know the segment here. I don't know either of these two mini segments. So I'm going to have to do some logical thinking here. So I do know that segment CD here in purple is a radius, the same as CB. So if CB is 8, that means that this is 8. So if I wanted to calculate the measure of AD, if I am thinking aloud here, AD plus DC equals the length of AC. Okay, so if I combine those two segments together, segment AD plus segment DC equals AC. So if I reverse that, if I reverse it and think about it like this, x plus 8, because that's the length of DC, equals 17, I can figure out that x here equals 9. So the length of the external segment here, using tangent Pythagorean theorem properties and a little bit of logic, states that AD, the external segment, must be equal to 9. Okay, so now we're going to do some angle finding. In the figure, TA and TG are tangent to the circle. Major arc AG is measured to be 220 degrees. What is the measure of external angle T? Okay, so they want us to find the angle over here. So we're going to have to do some logical thinking here. So let's think about it like this. There are 360 degrees in a circle. That's going to be important. And then we know, another fact here, we know that angle AG here, major arc, so major arc AG equals 220 degrees. And then we also know that AN and NG are radii that intersect tangents. So that last statement, AN plus NG are radii that intersect tangents, tells me that the two angles here are 90-degree angles, which will be important in a little while. The next thing that I know is I'm going to use the 360 degrees in a circle, and major arc AG is 220. So if major arc, and I'm going to have to do this in a different color, I keep switching colors here. If major arc AG here is 220, then the arc on the inside of the circle, and I'm going to redo that. The arc on the inside of the circle here would be 360 take away 220. Because the two arcs here, A and G, and then the long A to G, covers the entire length of the circle. So the entire 360 degrees in a circle, take away the amount we already have of 220, leaves us with 140 degrees for the arc on the inside. And then that would transfer directly to the central angle in here, because arcs and central angles are congruent, recall from section 8.2. So now I have a kite. So I have a kite with three angles. 140 plus 90 degrees plus 90 degrees again. And then we have an unknown measure, and we know that because it's a kite, that has to, all the four angles would add up to 360 degrees. So I can just go ahead and add 140 plus 90 plus 90, and I get 320 degrees plus x equals 360. So if I subtract 320 from both sides, I get x equals 40 degrees. So the measure of external angle T is 40 degrees. Okay, so now we're going to do some more. We're going to continue to do some more tangent work here. It says in the figure below, AD and BD are tangent to circle C. What is the value of x? Okay, so we're again going to run through the things that we know. We know that AD and BD are tangents, and both converge to D. And so if that is the case, we're going to use the property that two converging tangents are congruent. If two converging tangents are congruent, then I could say that the expressions that represent them are equal. So x squared plus, or excuse me, x squared, not plus, x squared in this case would equal 25. And so to solve for x, we would take the square root of each one, and x would equal 5. So the value of x here is 5. Okay, in circle Q below, chord TU intersects rays VS and VR. Rays VS and VR intersect at a point external to the circle at a 70-degree angle. What is the measure of VUT? So the angle that we are searching for, I marked with red. It is also marked with an X. And so in circle Q below, chord TU intersects rays VS and VR. And from the look of it, we have a triangle. So the next thing that we are going to do is that we are going to use that triangle to our advantage. We are also going to draw in some tangent or some radius segments, excuse me. So we have a radius from here to here. You'd have a radius from here to here. We could throw in. We do know, excuse me, that this segment and this segment are congruent, as are these and these. And we're going to utilize the properties of congruent segments. So I'm going to use some text here. So VT is congruent to VU. We also know that shape VTU is a triangle with congruent sides. That makes VTU a isosceles triangle. And that would mean that angle VTU is congruent to angle VUT. Okay, so with all that information in play, okay, we did a bunch of logical inferencing here. That means that I can mark this with an X as well. So in this shape here, and it turns out that the radius drawing was unnecessary, I would know that 70 degrees plus angle X would equal 180 degrees, since we're talking about a triangle. Triangle VTU is a triangle, or shape VTU is a triangle. So I would get 70 plus 2x equals 180. So subtracting 70 from both sides would get me that 2x equals 110. So x would be 55 degrees. So the segment in here would be 55, or the angle in here would be 55 degrees, as would this one. And then a little bit of just bonus information finding. We could then say that the measures in here, because we know that these two angles have to add up to 90 degrees. This would be 35 degrees in here, because that's 90 minus 55. So we could go ahead and find those measurements as well. And then finally, in the figure below, AB is externally tangent to circle C at A and circle D at B. What is the measure of segment AB? Okay, so this one is a challenge problem, guys. But I did want to go through it because I've seen these before. And so we're going to go ahead and kind of just bear with me on this one here. I'm going to draw some lines in. I'm going to draw this line in here, and I'm going to take my pen, and I'm going to put a big red dot here. I know that this segment here is 8, because this radius is 8, and they would be congruent. And then I know that this segment and this part would be 4. So I have an entire segment length, so I'm going to mark it down here. DC equals 12. And that's going to be important. The next thing I'm going to do is draw another segment. Because I'm trying to get some shapes where I know some more of the length here. So I'm going to draw from here all the way over. And I actually need to move the congruent markings here. This shape here is now a parallelogram. And I know this because this angle here is 90 degrees. This one here is 90 degrees. So this is 90 and this is 90. So I have a parallelogram, which means this segment here is congruent to this segment up here. And the 4 in here is congruent to this segment over here. So this is 4, meaning this miniature segment down here is also 4. So we have 4 here, we have 4 here, and DC is 12. The unknown length that I am dealing with is here, X, because these segments must be congruent. I know this forms a 90-degree angle, so I have a ton of right angles. I have a right triangle, and I have a parallelogram. The right triangle and the parallelogram share a side, X. So if I could use right triangle trig, or actually I could use the Pythagorean theorem to find X, then I would know X, the external segment. So let's do the Pythagorean theorem here. 4, this segment down here, squared plus X squared is equal to DC squared, which is 12. 12 squared. So I get 16 plus X squared equals 144. So I get X squared is equal to 128. And so we are going to just approximate that. We're going to use an approximate answer. The square root of 128 is 11.3. So X is equal to approximately 11.3. So this problem was just one set of Pythagorean theorem. The most complicated part of it was actually applying properties like the radius, knowing to connect the segment, and then drawing this segment in here. This is why this is a challenge problem, not kind of my expectation, but it gives you a good overview of how you can use tangents with the 90-degree thing. You can use the equal radius things here to construct and then solve for missing sides in a shape. So that's it, guys. A little bit of a longer video today. In summary, we learned what a tangent is and a point of tangency, as well as the name of segments that go through a circle twice, secants. We learned that tangents form 90-degree angles with the radius of the circle that they touch. We learned that tangents that converge to an external point are congruent, and then that helps us form kites with the radius. And we learned how to apply the Pythagorean theorem to tangents and find angle measures that are created by those tangents. So that's it for the video, guys. Thanks for watching and sticking with me for this one. That's it for Chapter 8, and I will see you in the next video.